Okay, so here's the second video in this series, although I guess the first had some issues. Hopefully we got that ironed out for this one. We're just going to talk today about definite integrals. So my goal today is just to basically remind you about definite integrals. What makes it definite is that there is a beginning and an end to that. And so when you see that term to evaluate this definite integral, or you see the term definite integral, don't let that trip you up. It simply just means I'm giving you a beginning and an end. This lovely little symbol that looks somewhat like an S came from Newton back in the 1600s, and it represents very similar to summations, but it's recognizing the patterns that occurred when we found the area underneath curves and the shortcut that it actually represents as well. Now this area that it represents, this integral that we're evaluating here, technically represents the area above minus the area below. Area itself is positive, that you can't have necessarily a negative area. However, integrals can be negative because it accounts for the positioning as well. Basically, when you're evaluating an integral, what you're saying to them is there is more area above or there is more area below, given whether it's positive or negative, respectively. So as you can see from this little drawing here, this picture, it kind of illustrates that. It would be positive if there was more area above than there would be below. And obviously that, if we were just evaluating in this case from -2 to, I don't know what you would say that is, but, I guess -1 to, let's say, 2.5, you would see that that area, or that integral, excuse me, would be negative, indicating that it was falling below the x-axis. With that in mind, if I was to ask you to evaluate these such functions, which this is just simply saying, given f of x, which is this graph that you see here on the board, evaluate from 0 to 2. What it would be asking you to do then is to determine the area for this little trapezoid that you see here. And so one option is to basically break that into two sections. So you'd have a rectangle, a 1 by 2, so the area of that rectangle being 2, and then find the area of that triangle, which looks as 1 times 2 divided by 2, or rather is 1. So together would make 3. If I asked you from 0 to 3, on the other hand, now you have this triangle here, which again is also the area of 1, but that would mean we'd have from 0 to 3. So you'd have the area, which is the 2 plus 1, or 3, and then you'd subtract 1. And so that would give me 2, for obvious reasons. If I was to ask you to do from -2 all the way to 8, then I'm adding up all of these areas, and anything that's above we would consider as being, of course, positive. So we've already established that that trapezoid section there is 3. I'm going to leave that as 3. This here is 2 times 2 divided by 2, or rather is 2. We have this triangle now to go from 2 to 8. Of course, that length is 6. The height here is 4. 6 times 4 is 24. Divided by 2 is 12. You make that a big 12. And so you can look at it two different ways. You could say, okay, that's 6 minus 12. Or you could say, okay, that's 6 plus, and then the position of that would be -12. Regardless, you get the same response, and that is -6. If I instead expanded this to be -2 to 10, that would now add in this circle. And of course, hopefully we don't need this reminder, but I'm going to throw it up there. An area of a circle is area equals pi r squared. Apple pies are 2. Remember that? Chocolate pie, delicious. Apple pies are 2. That's the way to keep circumference and area straight. Hopefully that's something that rings a bell to you. So the area of this, the radius is 1, not 2. That would be the diameter. The radius is 1, so I'm going to do 1 squared times pi, or rather just pi. However, this is only half a circle, so it is pi over 2. So what does this look like then? That means I have -6, and that is above, so it's plus pi over 2, and that's about what you would see as an answer. Hopefully, just by you looking at the graph of this, you can see illustrated what that definite integral means, above and below. All right, so now what would this look like from 0 to 5? Now we're going to do it more of a graphic way than we are using the shortcuts that we learned last year, because I still want to zone in on what we're looking at here in terms of area above and area below. So this is representing the function y equals x minus 2. And so we're going to actually graph that as being negative 2. And of course, that means your x part is positive 2. So here's what we're looking at. And if it's asking from 0 to 5, then that means we want the area of this all the way up to 5. And so it's 2 triangles. And hopefully we can evaluate that relatively easily. So that's 2, and that's 2. Making 4 divided by 2, that area is 2. This section here is 3. And the height of this, how would I determine the height of that? Plug it into that equation. Well done. So that would mean this is 5 minus 2, or rather this height is also 3. So 3 times 3, which is 9 divided by 2. So what I have here is 9 halves minus 2. Obviously, you wouldn't see an answer like that. You would have to get that common denominator. And so we really quickly discovered that the answer to that is 5 halves, is the integral from 0 to 5. Okay? Good. Now, just as a quick recap, and especially since that video did not work, how do I evaluate Riemann sums when we have this equation? So it's gotten a little bit more in depth. The previous ones were definite integrals, and we could do those graphically because we could actually look at this. But this is a parabola. This is some quadratic that's going to have a curve to it. It's not straight lines, nice boxes and triangles and stuff like that. So what we've got to be able to do is use Riemann to approximate this. Eventually work into being more exact, but for right now, that's what we'll have to do. So left hand, 4 subdivisions, what are we going to do? Well, as you talked about yesterday in the video as well as in class, we looked at the fact that you want to first discover the length of the interval. And of course, the length of the interval is determined by these numbers right here. This is the beginning and this is the end. So negative 2 to 6, that means the length of this interval that we're talking about is 8. So if I want to divide it into 4 subdivisions, that means the width of every single bar would be 8 divided by 4, or 2. And that means that I'm going to have to come up with 4 heights, because there's 4 subdivisions, that means there's 4 heights. To determine those 4 heights, that's the next piece. Now again, our interval starts at negative 2, and we want to get to 6. I want 4 subdivisions. So what that looks like here is, I want 1, 2, 3, 4 subdivisions. I need to figure out what these next numbers are. We've already determined that the width of every one of these bars is 2. And so we're going to add 2 to this. Sorry, I put the 2 in the wrong spot. And that makes this spot 0. Then I add another 2, and that's 2 and 4. And you can see that it would land perfectly on 6. So that means the height of my first bar, if we're talking about left hand, would be determined at f of negative 2, the left-hand side of that bar. This would be the first bar. Then the next bar would be at f of 0. The next would be at f of 2. And the next would be at f of 4. And we would plug in those values into the equation and see what the heights are at each of those spots. Now, if this said right hand, instead, on the alternative, we would have had f of 6, f of 4, f of 2, and f of 0. You'll notice that we didn't use the left farthest point because we're going from the right-hand side. So I'm going to just quickly fill in what those are. I encourage you to do the same. Go ahead and pause and find what each of those values are. Okay, so hopefully for each of the heights there, you got 26, 4, 6, and 32. And so now what we would do is, of course, we would add up those numbers on the inside. Give me 36, 68, and we would multiply by 2, which gives me 136. Okay, now if I wanted right-hand Riemann sum, but this has 2 subdivisions. So back to the drawing board. We're going to look at the length of the interval, which is 8. I'm going to divide by the number of subdivisions. Oops, forgot my G. Length divided by the number of subdivisions, which is 2. And that means the width of every bar is going to be 4. So if I'm looking from negative 2 to 6, and I'm splitting it into 2 subdivisions, that means this bar is worth 4, and so is this one. So negative 2 plus 4 is 2, and then 2 plus 4, of course, lands at 6. So that means if I'm doing right-hand Riemann sum, that means that I'm going to do f of 6. That's the right hand. And then I'm going to do f of 2, the right hand of that side. And then we work that way. Okay, so then I would have to plug in f of 2, which we already know what that one is from the question above. And then we do f of 6, which that's 36 times 3 minus 15 plus 4. So you get 97. You add the 2 together, to get 103 times 4. And so you get 412. Yikes. We're getting some crazy numbers here, aren't we? And we'll look eventually on how we can find the exact value of these. But for now, that's what we're looking at. And that wraps up this session that I wanted you to look at. So today, you should have looked at definite integrals graphically, and then just another way of looking at Riemann sums without the picture, without the graph. How do we work that? And being able to split up the interval and the subdivisions. Okay, good luck, and we'll be practicing some more of this in class.